In this video, we're going to take a look at exam revision for algebraic methods. So this is the first year material on algebraic methods. If you are looking for the second year material on algebraic methods and that exam revision video, we do also have that video, and I'll link that down in the description below. But for this video, all we're going to do is just take a look then at some first year exam style questions for algebraic methods. As always, pause the video, have a go at the questions they appear, and then double check that your solution matches what we get on the screen. Other than that though, I think that's everything that we need here to get started. Let's begin now with question 1. Starting off with question 1 then, where we have a question here on the factor theorem. Now this question is broken down into 3 parts, and the first part, part A, is actually a question on proof. So part A says, prove that if x minus q is a factor of f of x, then f of q equals 0. So where do we begin here for part A? So for part A then, well, we have the function f of x. So I've got f of x here. Now, if x minus q is a factor of f of x, what that means then is we can express this here as a product. So I would have x minus q. We've got x minus q, and I can times this now by some polynomial, which we're going to call g of x. So I've got this x minus q here, this factor, and I times this by some polynomial, which we're going to call g of x. Okay. Now, using this key concept here of the factor theorem, well, if x minus q is a factor of f of x, then f of q equals 0. So in that case then, if we have f of q, if I have f of q here, I simply replace any x's with q. So here we get q minus q, and we times this here by g of q. Okay, well, q minus q, that would be 0. So in that case, then what we get here is 0 times g of q. But this here then must be equal to 0, because anything times by 0 is equal to 0. So that is equal to 0. So therefore, in that case then, so therefore f q equals 0 as required here. Okay, so as required. And there we have it. So that's the proof complete there. So it's a pretty short proof, not too much work involved, and it just comes from this key fact here. Okay, so like I said, then just breaking down this function f of x into this product here, and then using the factor theorem. Okay, so there we have it. So that's the solution to part A. So for part B then, we're now actually going to use the factor theorem. So it says, hence show that x minus 1 is a factor of f of x. And we've got our function here, f of x. So if x minus 1 is a factor of f of x, so if x minus 1 is a factor, and what that means here is f of 1 equals 0. Okay, so all I'm going to do here then is substitute 1 into this function here. I'm going to get f of 1, and that is equal to 1 cubed. We get 1 cubed there, plus 4 lots of 1 squared, plus 4 lots of 1 squared. Then got plus 1, and then finally minus 6 there. And now if we simplify this here and evaluate this, well, 1 cubed is 1. 4 lots of 1 squared, but 1 squared is 1. So 4 times 1 is 4. I've got the plus 1 here. And minus 6. Well, 1 plus 4 is 5. Plus another 1 is 6. Minus 6, that gives us 0. So that's equal to 0. So therefore, in that case then, so therefore, x minus 1 is a factor of f of x. Okay. And there we have it. So that's the solution to part B. Now finally for part C here, it says express f of x as a product of 3 linear factors. So this comes back now to this concept here. So we can express this as a product. So I've got x minus q times g of x, where g of x is some polynomial. Now in this case, because f of x here, this polynomial here, this is a cubic polynomial. When I break this down into this factor here times by this new polynomial here will be a quadratic, because this factor here is a linear factor. It's got a power of 1. So in that case, then this would be a quadratic. Okay, so what do I mean by that? Well, let's just show that mathematically. So f of x here is equal then, so that's going to be x minus 1 times by some quadratic here. So if we just use the general equation here for a quadratic, that would be ax squared plus bx plus c. And then obviously what I want to do then, once I obtain the quadratic here, is hopefully factorize that quadratic and express then f of x as a product of 3 linear factors. So let's just obtain the quadratic to begin with. So what we have here is x cubed plus 4x squared plus x minus 6. So in that case then, let me write down the full expression, and let me just clear the screen actually. I think it's going to be a bit easier with a bit more room. I'll just clear the screen then. So for part C then, like we said, this cubic here, so x cubed plus 4x squared plus x minus 6 here, that is equal then, so our factor here was x minus 1. And we times this here by some general quadratic, so ax squared plus bx plus c. Okay, so basically what we need to do here is identify the value of a, b, and c. Well, there's a few different ways you can do this. The first way would be to use algebraic long division. And that way is absolutely fine if you use algebraic long division. So you divide in this cubic here by x minus 1. You can do that, and that would give you this quadratic here. The other way that you can do it in the way that I'm going to do in this video is by inspection and equating coefficients. Now, this way might seem a little bit complicated at first if you've not been shown this, but I find it a little bit easier and it saves a bit more time. So what I'm going to do here first is identify the value of a and c. So the value of a is easy to identify here because if we think about this for a moment, x times ax squared, well, that would give me the x cubed term here. There's no other way to obtain x cubed. So in that case then, because the coefficient here of x cubed is 1, that means a must also be 1. Because x times ax squared, that would give me ax cubed. So equating coefficients then, I've got ax cubed is equal to x cubed. In that case then, a must be equal to 1. Okay, so that's the first part done there. So we've got the value of a. Then for c, again, this is easy to identify because minus 1 times c must be equal to minus 6. So minus c is equal to minus 6. So therefore, c would be equal to 6 because minus 6 divided by minus 1 gives us 6 there. So all that's left to identify now is the value of b. And this is a little bit more complicated, but nothing too challenging here. So the way that I'm going to identify this here is by equating coefficients for x squared. So what do I mean by that? Well, if we think about this for a moment, how do I get any x squared here from this product? Well, I've got minus 1 here times ax squared. So it would give me a term there involving x squared. I'd get minus ax squared there. But we know that a is 1. So I'm going to get minus x squared. Let me just write this down again so you can see it a little bit easier. So I've got x minus 1 times x squared, because we know a is 1, plus bx, and then plus c, which is 6, like so. Like we said then, minus 1 times x squared, that's minus x squared. How else do I get a term here in x squared? Well, I'd do x times bx here. So that would be plus bx squared. And there's no other way then to get a term here involving x squared. So now we can equate coefficients here. So we know my x squared term must be equal, so the coefficient must be equal to 4. So this is equal to 4 then. And now if we equate the coefficients here, minus 1 plus b is equal to 4. So all I've done here then is equate coefficients, and then if we solve for b here, b is equal to 5. Okay. So in that case then, what we get here for f of x is the original factor of x minus 1 times by now our quadratic polynomial here. So I've got x squared, b is 5, so that's plus 5x, and then we've got plus 6, so x squared plus 5x plus 6. But we're not done here because we want to express this as a product of three linear factors. So what that means then is we now need to factorize this quadratic here into double brackets. So we're nearly done. Let's just do this last step here then. So we get x minus 1. And thankfully, this is a nice easy quadratic to factorize. I'm going to get x plus 2 times x plus 3. So I get x minus 1, x plus 2, and then finally x plus 3. Okay, and there we have it. So that's f of x there expressed as a product of three linear factors. And there we have it. So that's the solution there to question 1. Moving on to question 2 now, where we have a very brief question here on algebraic fractions. And truthfully, this question here wouldn't look out of place on a bit of a trickier GCSE paper. So this question really is pretty straightforward. So all I want to do here is simplify this algebraic fraction. So what I've got here is 32y squared minus 2 all over 4y squared minus 31y minus 8. So where do we begin here? Well, remember, when you're simplifying algebraic fractions, what we want to do is factorize the numerator, factorize the denominator, and then cancel any common factors. So let's start with the numerator here, a little bit easier to factorize. So let me just write down the original algebraic fraction. I've got 32y squared minus 2, and that's all over 4y squared minus 31y minus 8. So let's start with factorizing the numerator then. Well, the first thing that I can do here is factorize the 2. So here then I'm going to get 2 lots of 16y squared minus 1. And that's all over 4y squared minus 31y minus 8. Now I'm not going to factorize the denominator just yet. So I want to carry on here with the numerator, because what I notice now is I have 16y squared minus 1, and that is actually the difference of two squares. So here then we can write the numerator as 2 lots of 4y plus 1 times 4y minus 1. Okay, and now let's factorize the denominator, and we can now see that the denominator here must have either a 2, a 4y plus 1, or a 4y minus 1. Because if it doesn't have any of those factors, then there's nothing that we can cancel. In other words, we can't simplify this fraction here. So it clearly won't be a 2, because this here is a quadratic and it's going to be double brackets, so it won't be the 2. So we're either going to have a 4y plus 1 or a 4y minus 1. And if you just think about this for a moment, it must be 4y plus 1, because it's going to be 4y plus 1, because I need to times this here by y minus 8. So if you want to double check that, you can expand that out and you'll find that you get this quadratic here. So 4y squared minus 31y minus 8. So from here now, we can now see the common factors that we can cancel. I've got a 4y plus 1 here in the numerator, a 4y plus 1 here in the denominator. So we cancel both of those. And what I get left with then is 2 lots of 4y minus 1 all over y minus 8. Okay, and there we have it. So that's the solution there to question 2. Moving on to question 3 now, where we have a question here on mathematical proof and methods of proof. So for the first part then, part A, we're asked to show that m equals n squared plus 5 is not a multiple of 5, where n belongs to the integers. So that's what this means here. So n belongs to the integers, and n is between 1 and 4 inclusive. So we're including both 1 and 4. So the first part here, part A, is based on proof by exhaustion. So what we need to do then is exhaust all the possible cases. So that would mean n equals 1, n equals 2, n equals 3, and then finally n equals 4. So for part A, we have m equals n squared plus 5. So n squared plus 5 then. And this is for n equals 1, 2, 3, and 4. So let's start with when n equals 1. That's the first case here for part A. So when n equals 1, what we need to do then is substitute that into this equation here. Well, m is equal to 1 squared plus 5. 1 squared plus 5. So that's equal to 6, and clearly 6 is not a multiple of 5. So it doesn't work for n equals 1. So it's right here, not a multiple of 5. So that's the first case. So then the second case here is when n equals 2. So when n equals 2, we get that m is equal to 2 squared plus 5. And that would be 4 plus 5, which is 9. And again, this won't be a multiple of 5. Not a multiple of 5. And like you can see, proof by exhaustion is a little tedious, but we just keep going here. So when n equals 3. So when n equals 3, m would be equal then to 3 squared plus 5. So 3 squared plus 5, so that's going to be 9 plus 5, giving me 14 there. So again, that's not a multiple of 5. And then finally, my last case here is when n equals 4. So when n equals 4, m is equal then, so it's going to be 4 squared plus 5. Get 4 squared plus 5. Well, 4 squared is 16, plus 5 gives me 21. And again, that's not a multiple of 5. Okay, so not a multiple of 5. And there we have it. So we've exhausted all the possible cases then for part A. So basically all we need to do now is just give a quick conclusion here. So therefore what we say here is m equals n squared plus 5 is not a multiple of 5, where n belongs to the integers and n is between 1 and 4 inclusive. So let me just write that down here dead quick. So m is equal to n squared plus 5. This is not a multiple of 5. This is not a multiple of 5. Where n belongs to the integers. Where n belongs to the integers. And n is between 1 and 4. Okay. And there we have it. So that's the solution to part A. So what I'm going to do now is I'm just going to quickly clear the screen just so we can have a go at part B. So part B is also a proof by exhaustion. So here I want to prove that n squared plus n plus 5 is a prime number for n being between 0 and 3 inclusive. So again, this is a proof by exhaustion, so we need to exhaust all the possible cases here. So for part B then, my possible cases are when n equals 0, n equals 1, n equals 2, and then finally when n equals 3. So let's start with when n equals 0. When n equals 0, we're going to get 0 squared plus 0 plus 5. So 0 squared plus 0 plus 5. Well, that would be equal to 5, and 5 is a prime number. Let's just write that to the side. 5 is prime. So we're off to a good start. Let's carry on then. So when n equals 1. When n equals 1, what would we get here? Well, I'm going to get 1 squared. We get 1 squared plus 1 plus 5. So that would give me 7. And again, 7 is prime. We keep going here then. So when n equals 2. What would we get here then? I'm going to get 2 squared plus 2 plus 5. That's going to be 4 plus 2, so that's 6 plus 5. That gives me 11. And 11 is also prime. And then finally, we arrive at the very last case here, so that's when n equals 3. So when n equals 3 in this case, I've got 3 squared plus 3 plus 5. That's 9 plus 3, so that's 12 plus 5, that gives me 17. And finally then, 17 is also prime. So all the cases here satisfy this condition then, so we get a prime number each time. So therefore then, n squared plus n plus 5 is a prime number for n being between 0 and 3 inclusive. Let's just write that down to finish with for part B. So therefore, n squared plus n plus 5 is a prime number for n being between 0 and 3. Okay, so there we have it. So that's the solution to part B. And then finally for part C here, this is a disproof by counterexample. So here it says disprove that n squared plus n plus 5 is a prime number for all n greater than or equal to 0. So notice this is pretty similar to part B. The only difference here now is this is for all n that is greater than or equal to 0. So for part B, it was restricted to n being between 0 and 3. And in that case then, because we used proof by exhaustion, we exhausted all the possible cases, and we showed that it was a prime number for all those cases. Whereas here now, we just need to find one case that disproves this statement. Okay. So we've exhausted from 0 to 3. So I think the most logical step then is to begin with n equals 4. So when n equals 4, what would we get here? I'm going to get 4 squared plus 4 plus 5. We get 4 squared plus 4 plus 5. Well, 4 squared is 16, plus 4, that's 20, plus the 5, and that gives me 25. So that's equal to 25. But 25 isn't a prime number because we can express that as 5 times 5. So here we're going to say, how can I write this? So 25 is not a prime number. So 25 is not a prime number. Therefore, this disproves the statement. So this disproves that n squared, let me just write it in full here. So n squared plus n plus 5 is a prime number so it's a prime number for all n greater than or equal to 0. Okay. And there we have it. So that's the solution to C. And that gives the solution there to question 3. Moving on to the very last question now, question 4, where we have a question on everybody's favourite topic, algebraic long division. So I've got this function here, f of x, which is equal to this cubic polynomial. We want to find the remainder when f of x is divided by, so for the first part then, part A, x minus 2. So for part A then, setting up the bus stop here for algebraic long division. We've got x minus 2 on the outside. So x minus 2 on the outside. And then underneath the bus stop here, we've got 3x cubed. We then got minus 5x squared. Minus 26x. And then finally, minus 8. Okay. So to begin with here, we take this largest power, 3x cubed, and we divide that by x. What would that give us here? So in other words, what do I times x by to get 3x cubed? Well, that would be 3x squared. So we put that on top. So we get 3x squared there. And what I do now is I take the 3x squared here that we've just obtained, and we then times it by x minus 2. So that would give me 3x cubed. And then 3x squared times minus 2, that would give me minus 6x squared there. Okay, what I do now is I put a line underneath here, and now we're going to subtract here. So ignore the minus 26x and the minus 8 for now. I've got 3x cubed minus 3x cubed, so they'll cancel. That'll just give me 0. We then got minus 5x squared minus 6x squared. So that's just the same as adding 6x squared. So minus 5x squared plus 6x squared, that simply gives me x squared. So we get x squared there. So now what we do here is we take x squared and we divide that by x. So x squared divided by x, that would simply give me x. So we get plus x there on its own. And now we just repeat this process here again. So we take the x here and times it by x minus 2. So x times x minus 2, that would give me x squared. Oops, I've just forgot one step here. We now need to bring down the minus 26x here before I continue. So we bring that down here like so. And then, like I said, we take the x here and times it by x minus 2. So that gives me x squared and minus 2x. Like so. Again, we put a line underneath here. And now we perform the subtraction here. So x squared minus x squared. So that would be 0. Minus 26x minus 2x. That's the same as adding 2x here. And that would give me minus 24x. We get minus 24x there. And now what we do is we bring down the minus 8 here. So we get minus 24x minus 8. So now what I do here is I take the minus 24x and divide that by x. So minus 24x divided by x, that gives me minus 24. Get minus 24 there. And now we just repeat this process that we performed 2 times now. So here and here again. So minus 24 times by x minus 2. So I'm going to get minus 24x. So minus 24x and then minus 24 times minus 2. That gives me positive 48 there. So plus 48. And now we put a line underneath one more time, and then we perform subtraction here. So minus 24x minus 24x, they just cancel. Then we've got minus 8 minus 48 here, and that gives me minus 56 there. We get minus 56, and therefore the remainder then so the remainder for part A is minus 56. Okay, and there we have it. So that's the solution to part A. So the remainder is minus 56 when f of x is divided by x minus 2. So now let's have a go at part B. So we're just repeating this process here again, but this time now dividing f of x by x plus 2. So again, just setting up the bus stop here. We get x plus 2 on the outside. We've got our bus stop here, so we've got 3x cubed minus 5x squared minus 26x, and then finally minus 8. So we just repeat this process here that we just performed for part A. So we take 3x cubed and divide that by x, and notice we'll get the exact same here, so I get 3x squared. So I get 3x squared here, and now we take the 3x squared and times it by x plus 2. So here I'm going to get 3x cubed, because 3x squared times x is 3x cubed, and then 3x squared times 2, that gives me positive 6x squared there. We get plus 6x squared. Now what we do is we put a line underneath here, and now we perform the subtraction here. So 3x cubed minus 3x cubed, that would be 0, minus 5x squared minus 6x squared, that would give us minus 11x squared. And what we do now is we bring down the minus 26x here. Got minus 26x here. So now we take the minus 11x squared and divide that by x, and that would give us minus 11x. Okay, so we get 3x squared minus 11x here. So now we repeat this process here that we just performed. So minus 11x times by x plus 2. I get minus 11x squared. And then minus 11x times by 2. That gives me minus 22x. Okay. So we put a line underneath here. And now what we do is we perform our subtraction here. So minus 11x squared minus 11x squared, that would be 0. And we've got minus 26x minus 22x. That's the same as adding 22x here, and that would give me minus 4x. Okay, so we get minus 4x there. Now we bring down the minus 8 here. And then finally, we're nearly done here. So we've got minus 4x. We now divide that by x here. So minus 4x divided by x, that would give me minus 4. So I get minus 4 there. And now we take the minus 4 here and times that by x plus 2. So again, you can see this is quite repetitive, but there's nothing particularly too challenging with this. You just have to be careful with the signs. That's usually where people make the silly mistakes. So minus 4 times x here, that'll give me minus 4x. Minus 4 times 2, that'll give me minus 8. So we put a line underneath and perform the subtraction here. Well, minus 4x minus minus 4x, that would be 0. And then minus 8 minus minus 8, that would also be 0. So we get 0 there, and therefore the remainder when f of x is divided by x plus 2 is 0. So let me just write that underneath. So therefore the remainder for part B is 0. Okay. And there we have it. So that's the solution to part B. And that gives us the solution there to the very last question, question 4. And that brings us to the end of this video on exam revision for algebraic methods.